In this video, I'd like to walk you through our last set of notes. And I really do mean our very last set of notes. I'll be honest, I'm a little bit disappointed that our last set of notes is taking place in a pre-recorded video instead of in class or in a Zoom session. But I guess just circumstances kind of worked out that way. But I put here a piece of paper in front of the notes because I want you to see where we are in the big picture. In an ideal school year, I like to get down to what I call Unit 18, which is Atomic and Nuclear Physics. And I like my very last set of notes to be E equals MC squared, because it would really be nice for you to walk out of high school physics and have a better understanding of what that equation is and where that comes from. But really, this last set of notes that you and I are going to be looking at today is really what would be the first set of notes under the topic of light. So you just did a little overview of waves and sound. And now we're going to contrast sound to electromagnetic waves, of which light is one of those. But jumping ahead, after the unit of light, I like to talk about optics. Optics is an application of the topics in light. And in terms of a career, many people talk about wanting to go into a medical or a health field, but they don't always think about becoming an eye doctor or an optometrist, an optician. And I've seen that when I've covered the topic of optics, it seems like there's always one or two students who actually pursue that career field. So I'm kind of bummed that we didn't get to talk about that. But I do plant that seed for you. And then in Unit 18, which is Atomic and Nuclear Physics, this is an important topic in physics research today, and it's also where the equation E equals mc squared comes into play. So as you can see, by not getting this far, we are not going to get to the topic or the equation of E equals mc squared this year. So I'm a little disappointed about that. But those few who enrolled in Physics C next year, we may touch on these ending topics so that we can bring our first year of physics to close. So with that, we are talking about the topic of light, and this would be the very first set of notes in the topic of light, where we start to look at all EM waves and we organize them in a spectrum. So without further ado, let's start by looking at what are called fields in physics. So in physics, there's three different kinds of fields. There are gravitational fields, electric fields, and magnetic fields. So like, how do you get a gravitational field? Well, you don't really have to do anything, because around any mass is a gravitational field. So for example, around a planet is a gravitational field, and this could be a picture of a baseball, and around a baseball is a gravitational field. If you could take your body and roll it up into a ball, around you is a gravitational field. And if I want to draw a picture of the gravitational field, it would look like this. It would be arrows all pointing towards the center of the object, like pointing towards the center of the earth here. Because if I plop something in a gravitational field, the arrows show you what direction the object would move. So that's what my gravitational field looks like. So around masses, you have a gravitational field. So this is actually the word mass goes right here. Electric fields exist around charged particles or around charges. So for example, let's say that we had a positive charge. So I'll put a little circle around it here. So what does an electric field look like around a positive charge? Well, it ends up looking something like this. And the arrows go out. So the question becomes, how do I know the arrows point outward? So an electric field, the direction of electric field is you pretend that you have a positive charge. It's called an imaginary positive test charge. So you have an imaginary positive guy and you plop him in the field. And the question is, which way would he go? Well, because he's positive and this is a positive charge, he would be repelled. He would go this way. That's how I know that's the direction that the arrow points. If I put him over here, he would go this way. So that's how I know the arrows point outward from positive charges. If I had a negative charge like an electron, what would the electric field look like? And you can figure out what the electric field would look like by using the same imaginary positive charge. So I'm going to put a positive charge right here. And which way would he go? A positive charge would end up being attracted to a negative charge. So that tells me the electric field around negative charges are arrows that are pointing towards the charge, kind of looking a little bit over here like the gravitational field. But what's important here is that gravitational fields are arrows going towards the planet or mass. Electric fields are arrows going towards negative charges or away from positive charges. But magnetic fields exist around magnets. Magnets. So I'm just going to draw a magnet here for a minute. I'm going to draw what's called a bar magnet. And a bar magnet has like a south pole and a north pole. And the magnetic field that exists around magnets is not arrows that point inward or outward, but the arrows go from the north pole around like in a loop to the south pole. North pole to south pole, north pole to south pole. And I'll do some the other way, north pole to south pole. And it ends up looking something like that. So this is a picture of our Earth. And you may have heard the phrase before that our Earth has an iron core. Well, iron is magnetic. So the core of our Earth can be thought of like a bar magnet that has a north pole and a south pole. But if you looked at the iron core of our Earth, the south pole side actually is our north pole of our planet. So let me draw a planet like on top of the bar magnet. So our Earth behaves as if there's a bar magnet inside the core. And so the south side of the bar magnet is next to our north pole, and the north pole of the bar magnet is next to our south pole. And then you see these magnetic field lines going around our planet that are shown here in this picture. So why do you need to know about those? Well, it's interesting that some of you may have heard the phrase or maybe even seen the northern lights or the southern lights. The northern lights are obviously up here at the North Pole. And if you go up north, sometimes you can see the sky turns pretty colors and green. If you've never seen it, you can Google it, called the northern lights. From a scientific term, it's called the aurora borealis. And basically, the charged particles in the atmosphere align themselves with these magnetic field lines. And so the pretty displays that we get in our sky are because there are magnetic fields around our Earth and around any magnets. So all of that comes into play here in that we at one point tied together the topic of gravitation, which comes from mechanics, to the topic of electricity and magnetism through Coulomb's law. We wrote down that Coulomb's law, which was the electric force, was KQQ over D squared. And the gravitational force, which is part of mechanics, was GMM over D squared. And we just use that to show that there's a connection between these topics. There's a connection between mechanics and electricity and magnetism. And so now we have electric fields and magnetic fields, and we're going to bring them together. And when we bring them together, we end up with waves. And so now we're making a connection to the third topic area in physics, which shows that all of these things that we're talking about are so interconnected, but we don't really have all of the details. And it just shows how much research is still left to be done in the topic of physics to make all of this make much more sense to us. But what we know now, as of now, is number 2, is that all waves, electromagnetic waves, consist of an electric field and a magnetic field that oscillate perpendicular to one another. So in this picture here, it looks like this one that's going up and down. And when I say up and down, we'll picture this like on the y-axis. This is the electric field. So sometimes, like at this point right here, the electric field is the highest. But as time goes on here, the electric field is getting bigger and bigger and bigger, and then smaller and smaller and smaller, and then bigger and bigger and bigger, and then down here to trough, it's the biggest, and then smaller and smaller and smaller. So the electric field is constantly changing. At the same time, here we have coming out at us, I'll draw it like this. This would be like on the z-axis, is the magnetic field. And it also is getting bigger and bigger and bigger, and then smaller and smaller and smaller, and it is continually oscillating also. So we have a changing electric field, a changing magnetic field that are both changing perpendicular to each other. And if you actually click on this animated GIF here, you can see how the waves are, or how the fields are changing, and how that makes the waves seem to be traveling in this direction. So even the whole concept of what a wave is very, very complex, even much more complex than our discussion can take us there today. But where we can go with that, though, is we're going to introduce another scientist, and this is Mr. Maxwell. So Mr. Maxwell, he actually studied electric and magnetic fields, and he made some predictions. So he has 4 laws that you'll maybe one day learn about in college. But Maxwell's 4 equations end up with a mathematical prediction. So he predicted that the velocity of all waves, of all electromagnetic waves, they would travel at a velocity equal to 1 divided by the square root of 2 constants that are multiplied together. One of these constants, this first value here, actually comes from the concept of an electric field. The second constant comes from the topic of magnetic fields. So even though we did not study fields in enough depth to learn about the constants back in the day, we're going to pull those constants out here. And if we take those values, and I'm going to take the E naught value, and that is 8.85 to the negative 12. And we're going to multiply that by 4 pi to the power of negative 7. And then we're going to square root that. So square root of the answer, and then we're going to go 1 divided by the answer. And Maxwell predicted that all electromagnetic waves would travel at this number. And there's, if I move my decimal point over and round it off, we get 3 times 10 to the 8th meters per second. So back in 1865, we did not know the velocity of light or any electromagnetic waves. It was just a mathematical prediction from Maxwell's equations. And this just gives you a sense of how the math in physics, because of the mathematical predictions, we sometimes find that reality actually happens. And so kind of like the math actually drives the physics here. Number 4, I'm not going to talk about here right now, but it says the unit of frequency is named after Mr. Hertz. So maybe you can research and figure out what Hertz's claim to fame is, but he adds a little piece of our story here. So now it's the late 1800s, and we now are talking about waves traveling through space. So, for example, people knew that if I wanted to have a water wave, I'm going to need some water. And if I wanted to have a sound wave, I'm going to need some air. And so then we're talking about light in all of the waves in the electromagnetic spectrum. And scientists says, oh, well, electromagnetic waves, I'll write this up here, electromagnetic waves, they are going to need something to travel through. But nobody knew what it was. And so they gave it a name. They called it the ether. The ether. Technically, this word goes in this blank here. Sometimes it was called the luminiferous ether, and sometimes they spelled the word ether with an A in front of the E. But they were so convinced that light and all electromagnetic waves needed a substance through which to travel that they named it the ether, and they set out to try to learn more things about the ether. For example, they hypothesized that the ether was going to be colorless because we can't see it. It was going to be odorless because we can't smell it, et cetera, et cetera. So Michelson and Morley designed an ingenious experiment. And I give you some links here to kind of look and learn a little bit more about their experiment, but I'll kind of simplify it a little bit in a drawing here. So Michelson and Morley took the Earth like this and thought to themselves, we know the Earth is like, on this path going around the sun. And so let's just pretend at this exact moment, the Earth is traveling this way. So that would be like if you were on an airplane and you were going with the wind. And sometimes when you're on an airplane, you go against the wind and your trip takes longer because you're fighting the wind. But when I go with the wind, I kind of get where I'm going a little bit faster. So they pictured the ether is out here in space, and it's like in our air, and it's like everywhere. And there are times when my planet is going with the ether, then the light and the EM waves should travel faster. And there would be other times that our planet would be going against the ether, and then light and EM waves would travel slower. So they designed an experiment that way, way more complicated than I'm going to make it out to be here. But they went up to a mountain and they got a laser beam. So here we are on a mountain with a laser beam. And on a different mountain, they placed a beam splitter. So what that means is that the laser beam comes over here. And so like normally the laser beam would go straight, and at a different mountain, they put a mirror. And then the laser beam goes straight, comes over, hits the mirror, comes over here, hits this mirror, and then bounces back to here. But because I had this beam splitter here, when the beam goes over here, some of it went straight, but some of it bent and went this way. And so then at another mountain, they put a mirror here, and then this ended up reflecting off of this, and then it went through a hole in the beam splitter and it went this way. So on some of those links that I gave you here, there's much, much better pictures if you want to understand the setup of this a little bit better. But the point is that if I went over in this way versus if I went this way, for the light wave that went this way, I would be going with the ether, and I would have then presumably a faster path than when the light came back over here. So I made the light do different things. Sometimes I made it go with the ether, and sometimes I made it go against the ether. And that's what they were trying to do. They were trying to discover the ether. And then over here, they would measure the velocity of the light. But this experiment is supposedly the most famous experiment ever that had a null hypothesis. And those of you in stat may appreciate this. But they set out to do something and it didn't work. So many times when you do an experiment and you feel like it didn't work, you kind of like feel like you have to fix your experiment. But their experiment was a genius design of their experiment. And it was very quickly decided that it wasn't the experiment that didn't work. It truly was a null hypothesis. What they were setting out to do was not true. And so there were two key findings from the Michelson-Morley experiment. They were trying to detect the presence of the ether. Detect the presence of the ether. And what they found out is that there is no ether. No ether. That means that light and all EM waves do not need a medium through which to travel because we never found one. And also surprisingly to them, it didn't matter whether I was going with the direction of the planet or against the direction of the planet. The velocity of light was always the same. It was always constant. And that's where the C comes from. It was always constant. It was always 3 times 10 to the 8th meters per second. The idea that something, when you go with the direction of the planet and against the direction of the planet, and the velocity of light stays the same, has a lot of implications. And the E equals mc squared takes into account some of those things. So just a little tidbit, as you guessed, E stands for energy. C obviously stands for the speed of light, and now you know that value. And many people think M stands for mass. It kind of does, but it really stands for missing mass. But that's kind of a new idea, because conservation of mass says that mass cannot be created or destroyed. And in Einstein's equation, he says, but it was. It's missing. There's some mass that's missing. And so, again, this kind of is an extension of some of the things that we're starting to get into here. All right, so in summary, the Michelson-Morley experiment tells us that the speed of light is now going to be the variable v, or vc, as we talked about, and you know that the velocity of light is going to be 3 times 10 to the 8th meters per second. So even though we call that the speed of light, it is really the speed of all electromagnetic waves. So all of the waves that we're talking about today travel at this velocity. And when I say all of the waves that we're traveling about, I mean all of the waves that are down here in our EM spectrum. All right, before we get to our spectrum, though, let's talk about some of the implications of something traveling at the speed of light. So I'm going to write down velocity equals distance over time. And I can use this equation. This is our constant velocity equation, because the speed of light is constant, which means it's constant velocity. So it says the sun is an average distance of 1.49 times 10 to the 11th meters from the Earth. How long does it take light from the sun to reach the Earth? So we know that light travels at 3 times 10 to the 8th meters per second. The distance is 1.49 times 10 to the 11, and I want to find time. So I'm going to take 1.49 to the 11th, and we'll divide by 3 to the 8th. And it takes this many seconds for light to get to the Earth. But let's then go up here and let's take those seconds and let's turn those into minutes. And that is 8.3 minutes. 8.3 minutes. So that means when I look at the sun, I am looking at the sun as it existed 8.3 minutes ago, because it takes that amount of time for light to travel to my eyes. And so that's kind of interesting, because when you look at things that are really, really far away, you're not looking at them as they exist in the present. You are looking at them as they exist in the past. What if you were outside at night and you were looking at stars in the sky, like just little twinkly stars in the sky? So those are stars that could be even bigger than our sun, but they look so tiny because they're so far away. Let's just exaggerate and pretend that one of them was, millions of miles away, and it took, a million hours for the light to get to your eye. Then you are looking at a star. You are looking like further and further into the past. So on number 11, I talk about telescopes here. Many people think that the purpose of a telescope is so that you can see something like bigger and up close. So there's a little bit of that, but really the real power of a telescope is it allows you to look into the past. As I have a telescope and I can look at a star far, far, far away, I am looking at that star as it existed in the sky, maybe a million years ago. If I could have a telescope that's really, really, really cool or really, really big, I might even be able to look back and look at the Big Bang that is happening in the moment. And so there's a lot of kind of cool things about what we can learn from telescopes because we are looking into the past. So on number 9 that I won't go through here right now, it's the same thing, but you can see when you look at Pluto, how long does it take light from Pluto to reach us? And you are, again, sometimes I say, oh, I see the sun and I see Pluto, or I see Mars and I see Pluto. Well, you don't see Mars and Pluto at the same time because you're looking further into the past when you are looking at Pluto. But number 10, I'm going to do the same thing here because if we were in our classroom, this is always a good example here. So I always pick a student who's like the farthest away from me in the classroom. So let's pick somebody who's in the corner. I'm trying to think who's in the corner, 5th and 6th hour here. Allison, you're in the corner in the back there. So we'll say 8 meters away and we'll calculate the time. And I calculated this already. The time turns out to be 2.7 times 10 to the negative 8 seconds. So it's like light from the student in the back of the room hits my eye practically instantaneously, but technically 2.7 times 10 to the negative 8 seconds. So when I'm looking at that student in the back row, and in my mind, I can count up all the students in the room and say, oh, there's 30 people here. But you know what? I don't know if there's 30 people here in reality because I am seeing the student in the back row as they existed this many seconds ago. And maybe they left the room in those couple seconds and before the light got to my eye. And it just gives you a sense that we have a perception of reality. Like we open our eyes and we look all around us and we try to think that we're really, really careful and that we observe things. I think like in biology, we talk about, making observations. In chemistry, we talk about the scientific method is observations. And now I just want to throw a little twist in there and say that when you make observations, your observations may not be reality. Because when you're trying to take all those observations and look at them at the same time, because the light is coming to you from different distances, it's as it existed different times ago. And so in our brain or in our mind, we kind of put everything together and pretend that it's all truly in existence at the same time next to each other, but that may not be the reality. And so as you get deeper and deeper into physics, you really start to question, do we even understand anything around us at all? We have no perception of reality. It's just whatever our brain has conceived. All right, so moving on and kind of going with that thought here, we are now going to take all of the waves that we know about, light being one of them, and we are going to organize them in a spectrum. Okay, and a spectrum just means in some meaningful fashion. And so the meaningful fashion is usually in terms of increasing wavelength. So you can see that I take that back, decreasing wavelength. The wavelength here is pretty big, but when you get down over here, the wavelength is going to be really, really small. So the wavelength is big at this end and small at this end. Or you could look at this chart. Whoops, I'm even going off my page here. You could look at this chart and say that in terms of frequency, the frequency here is small. And the frequency is how scrunched together the waves are. And over here, they're very scrunched together. So these have big frequencies. And energy is going to end up matching the frequencies. So the waves at this end of the spectrum have small energies, and the waves at this end of the spectrum have large or big energies. And so waves of the electromagnetic spectrum are commonly organized into these little clumps. But I want to add another clump here. So the first wave that we want to talk about is going to be power waves. So I'm going to put these down here. And the reason I want to start with power waves is sometimes there are people who are afraid to buy a house next to power lines, especially like some of those big power lines that, take out a swath of land, that you can kind of look down that swath of power lines, for miles and miles. And some people are afraid to live there. And there are some studies that show that it can be dangerous. And there's other studies that show that no, it's not very dangerous. They're very low energy. You can see the way down here, low energy. And so in your homework assignment, you can research a little bit more about that. So power waves have the lowest energy, then radio waves, then microwaves, then infrared, and then visible light is this little section right here, ultraviolet. And so we call these waves, microwaves, infrared waves, visible light, not visible waves. And then when we get to ultraviolet, instead of saying the word waves, we usually change it to rays, and then X rays, and then gamma rays. But this is our EM spectrum. All of these waves travel at 3 times 10 to the 8th meters per second. The other thing I want to point out to you is the word infrared. Infra is a prefix, and the prefix infra means before. And so do you see that infrared means before red? It means before visible red waves. And ultra is a prefix that means after. So after violet rays. And obviously our visible light is our Rory G Biv. Rory, whoops, there's yellow, G and Biv. And I'll also point out to you that at some point, a group of scientists voted that Pluto was no longer a planet. At that same meeting, they voted to get rid of indigo because they said nobody really knows what indigo is. And if someone asks you, you usually say it's bluish, violetish. And so they got rid of it. So it's really Rory G with no I. Okay, the last couple of things that we'll look at here are just the calculations that go along with this. And the wave equation, C equals frequency times wavelength. So this is the velocity of the waves, but the waves that we're talking about are the EM spectrum that are always going to be 3 times 10 to the 8th. So we replaced the V with a C. So you ran into this equation in our last unit. So we just replaced that. And then we have E equals HF. This allows us to calculate the energy of the waves. So wavelength is going to come from here. Frequency you can get from here or from here. And then the energy you'll get from Planck's equation. So the C value is always going to be 3 times 10 to the 8th. And energy is proportional to frequency. So the bigger the frequency, the bigger the energy, because H is a constant. And H is a constant named after Mr. Planck, who is the one who discovered that these two things were directly proportional. He named the constant after himself, and it's a tiny number. Again, a tiny fudge factor. 6.63 times 10 to the negative 34. All right, so how do we use these? So here's a quick example. All right, it says, think of a radio station. So I'm going to think of the radio station 95.5. If you had given me call letters, I would have said, well, what number on the dial is that? And you would have said, oh, that's 95.5. And I don't know what the call letters for that are. All right, so it says, what is the frequency of the radio station? Well, when you say 95.5 on the FM dial, that is the frequency. So this is megahertz. Anything that's on the FM dial is megahertz. If you had given me a radio station on the AM dial, it's kilohertz. That's the AM radio stations. But this is an FM station. All right, so what is the frequency in SI units? I can't have megahertz. That's a metric prefix. So mega means times 10 to the 6th. So times 10 to the 6th hertz. So that is the frequency. What is the velocity of radio waves? Well, the velocity of all EM waves is 3 times 10 to the 8th meters per second. So if you want to find the wavelength, then we can just use this equation, 3 times 10 to the 8th. My frequency is 95.5 times 10 to the 6th, and I can calculate my wavelength. I did this earlier in my video that got stuck, and the wavelength turns out to be 3.14 meters. If we were in class, I would take out a piece of rope and we would spread that rope out 3 meters, or cut the rope to 3.14 meters, spread it out like this, and then kind of make a crest out of it and a trough out of it, so you can kind of get a visual of what that radio wave looks like as it's in our classroom, or as it's in your house, or as it's out in the air. So like every single radio wave, every radio station, like you are swimming through all of these waves out there. And to be honest, you're swimming through tons of stuff. You are swimming through power waves, radio waves, microwave. You're swimming through everything. And this little teeny sliver is all that you can see. Again, just another example of how our concept of reality is so narrow that we have not a clue what our world really, really looks like. There's so much that we cannot see there. All right, calculate the energy of the waves. If you want to know the energy of the waves, we can use Planck's equation, E equals hf. And we use Planck's constant, 6.63 times 10 to the minus 34. The frequency has to be in SI units. So again, I'm going to use the megahertz, but change them into hertz. And I can calculate the energy in joules. So we'll take a second to do that real quick. 6.63 to the negative 34 times 95.5 to the 6. And a radio station wave, how many joules do I get? Not very many. 6.33 times 10 to the negative 26 joules. That's not a lot of energy. So, I'm not really worried that that radio station is going to kill me as I walk down the street. But as you get higher up in the spectrum, like ultraviolet rays, X-rays, and gamma rays, especially when you get to gamma rays, it could kill you if it hits you. So pay attention to the joules as you compare those things. I won't do number 15. I'll let you do that one on your own. But an X-ray is going to have a lot higher energy. It's going to have a lot higher frequency. We know the velocity of X-rays, 3 times 10 to the 8th. And the wavelength is in nanometers. So the wavelength, nano, is a metric prefix times 10 to the negative 9 meters. So you can calculate those there. All right, and then the last one, just using your spectrum, you should be able to look at the picture here, and then just kind of number these and put them in order of something that is meaningful. All right. I'm glad we were able to kind of quickly talk through here. I will connect with you before the end of the school year as we talk about our career planning and our college planning. We did not get a chance to do our job shadowing this school year, but there are things that all juniors should be doing in the summer between their junior and senior year. And I thought that even though we didn't do our job shadowing, I'm going to pull the assignments that went along with that piece, and we will look at those for the last week or two so that we are back on track for the fall. Okay, I hope this helped you finish your notes, and then the homework assignment you'll see kind of stands alone, and you can probably even do the homework assignment without even completing all of the notes. All right, I'll catch you later this week.